Welcome back. Today we're going to talk about the algebraic representation of the transformations that we've been talking about and doing geometrically. So first let's discuss translation. So what I mean by an algebraic rule is a rule that I can perform, or an operation that I can perform on the original coordinates when I have performed a translation. So the way that it looks like using symbols. So let's say that I have a translation. So this was the pre-image, which is this purple image, and it's been translated to become this blue image. Now I know it's been translated and not, for instance, reflected, because if I look at the orientation has remained the same between the purple and the blue. And the only transformation that we've studied so far that maintains orientation is a translation, right? The A and the E, for instance, haven't been flipped around, they haven't been rotated. A is up and to the right of E, and A prime is again above and to the right of E in the image. So we know the orientation is remaining the same. So I know it's a translation. So let's say that I have original coordinates x comma y, and I move right by a certain amount of units, like A units. Well, x comma y, the original coordinates would, so since it's right, which is a horizontal movement, and it's a positive movement, so we're increasing the x value, what I would say that the new coordinate would be is x plus the certain amount that you move to the right, and then the y coordinate would remain the same. Okay, so a right movement of A units would affect the x coordinate but not the y, and it would increase it by A amount of units. Likewise, a left movement of A would take A away from the original x coordinate, but keep the y coordinate the same. So the x comma y would become, this arrow means become, would become, under this translation, it would become x minus A comma y. If I was moving up B units, well, that B units affects the, since we're talking about up and down in the next two things here, this affects just the y and not the x. So here, I would keep the x the same, but then I would add b units to the y if I were raising it up. And here, the original coordinates would become x comma y minus b if I were moving down. Okay? Okay, in order to figure out the algebraic representation for the coordinates based on the reflections, what I want to do is I want to draw you through a couple of examples. So example number one, my pre-image starts in quadrant 1. And let's say that from here I reflect over the x-axis. Okay, and I actually should have this as C prime. So instead of just being C, this should be C prime. So my original C starts out and it has the coordinate 7, 2. And my new C, after it's reflected over the y-axis, my new C has the opposite x coordinate, which is negative 7, and it has identical y coordinates as the original C coordinate did. So my y coordinates stayed the same, so reflection over the y-axis means that my y coordinates stay the same and my x coordinates change to their opposites. Now let's pretend that I didn't reflect it over the y-axis, but instead I reflected it over the x-axis. Okay. Well, C prime here in this situation becomes 7, negative 2. So what stayed the same after reflection over the x-axis is that the x coordinates stay the same and the y coordinates change from positive to negative. Right? The magnitude is the same, so the absolute value between the y coordinates are both 2, but the signs change to their opposites. Okay, that's when the pre-image is in quadrant 1. Let's say the pre-image is in quadrant 3, where both the x and y coordinates, so C begins at negative 7, negative 4. So both of the x and y coordinates are negative. If you reflect it over the y-axis, what ends up happening, let's write this a little bit bigger, C prime becomes negative 7, comma 4. So the x coordinates remain the same, that's over the x-axis. So again, we see that the x coordinates remain the same, just like it did before. So here, when I reflected it over the x-axis, the x coordinates remain the same. Same with this one. Okay, but what happened with the y coordinates is that it changed from negative to positive. Okay, so here it changed from positive to negative, and here it changed from negative to positive. Now let's say that it starts in quadrant 3 and it reflects over the y-axis here to become an image in quadrant 4. So here my C prime coordinate would be 7, comma, -4. So if I'm reflecting over the y-axis, what remains the same is the x coordinate remains the y coordinate rather remains the same of -4, and the x coordinate changed from negative to positive. So in general, okay, what we're going to say is that when it's reflected over the x-axis, the x coordinate actually remains the same, and the y coordinate becomes its opposite. Now, this rule doesn't say that if x is positive, it becomes negative. It says that, if y is positive, then y becomes negative. It says wherever y begins, whether y begins its life as a positive coordinate or, like in the second example, if the y begins its life as a negative coordinate, whatever it was originally, it becomes its opposite. So if y starts out negative, it becomes positive because it would be a negative of a negative number, which would mean it would be positive. If it starts its life as a positive coordinate, it becomes negative. Okay? And if you reflect it over the x-axis, or the y-axis rather, the x coordinate becomes its opposite and the y coordinate remains the same. Okay? So for instance, if I start with 2, -3 and it's reflected over the x-axis, it would become 2, +3. Okay? Because the 3 turns from negative into a positive. That's what this is saying. This negative here indicates opposite, not that it ends up as a negative. Okay, and finally, the algebraic representation of rotation. So in order to write this down, I wanted to just point out the same example that we had in the, well, we have actually two examples. So the first one is the same example that we saw in the rotation video. So this is if we had C double prime, it would be -7, -2. This is a reflection in 180 degrees, a rotation of 180 degrees. This is 90 degrees and it's counterclockwise. And this would be 270 degrees clockwise from the original image, actually counterclockwise. And this would be C triple prime to -7. Okay, now what happens with a 90-degree rotation, we've said this before, that the x's and y switch. Okay, so it becomes y, comma, x. Now let's see what happens with the sign. So if it's a clockwise rotation from here, let's say from here to here, if we presume that this was the pre-image and the yellow was the image, what happens with the sign? Well, the the thing that was originally the y that becomes the new x remains the same, but the thing that was the x before and becomes the y changes to its opposite. So here, for a 90-degree clockwise rotation, it becomes y, comma, -x. Okay, so if it were 90 degrees counterclockwise rotation, so here, the blue to the green would represent a 90 degrees counterclockwise rotation. Well, what happens here is the y and the x switch again, but the new x becomes its opposite. Okay, so if it's counterclockwise, we have y, comma, -x. If it's clockwise, it's y, -x. And if it's counterclockwise, it's -y, comma, x. Now, for the most part, you don't have to remember these rules for 8th grade as much as the rules for translation and reflection. Because rotation, we can always just think about them flipping for every 90 degrees and then thinking about whatever quadrant it lands in. That might be a little easier for you. But if you would like to do it by remembering the rules, that's also okay. All right, what happens with a 180-degree rotation is that the x and y's remain the same, but both of their signs flip to their opposites. So let's say if it started out in quadrant 4, they would x and y would remain the same, but the signs would be both positive because a 180-degree rotation would land it in quadrant 1, for instance. Okay? If they both start their life as negative, then they become positive with the switch. If they both start as positive, but they both become negative, and if one starts out negative, then it becomes positive with 180 degrees. And I wanted to show you one example of what happens with a rotation if the points that we start with are actually on the axes. So here, this blue one is the pre-image. And if I rotated it, let's see, this is 90 degrees counterclockwise. If I rotated it like this, then what you'll notice about A is it started its life on the x-axis. And after you have a 90-degree counterclockwise rotation, it jumps to the y-axis. Now B started its life in the y-axis, and after a 90-degree rotation, it goes into the x-axis. And this really makes sense because remember what we said before, that if we connect B, the original vertex, with the center of rotation, which is the origin, and we connect B prime with the origin, then the vertex and its corresponding vertex should create a 90-degree angle when connected to the center of rotation. So that's what ends up happening. Whatever it started off on the x-axis jumps to the y-axis under 90 degrees, and whatever starts on the y-axis jumps to the x-axis under a 90-degree rotation. And likewise, if you did a 90-degree rotation clockwise, B jumps to the x-axis because it started out on the y, and A, which started out on the x-axis, jumps to the y-axis. So don't worry if it starts out on one of the axes. It's not really a big deal because it just jumps to the alternate axis under every 90-degree rotation. Of course, a 180-degree rotation would have A and B be right here, so it would just look like something like this. Okay? And that is the end of the lesson for today.